something you may remember. So if I have an alloy that at ambient temperature, I have everything can be together as one phase. It's the case here for copper and nickel. So nickel is to the left, and then I got copper to the right. Copper has a lower melting point, and then nickel has a higher melting point. So if I have a concentration of a liquid that's somewhere on a line here, and I mean the idea is to form a solid. So we know at low temperature we're going to be solid, at high temperature we're going to be liquid. When I form the first solid, it will make sense that there's more nickel into it, because nickel is the higher melting point. And that's why we have that general phase, like a lens type of structure, where when I'm starting to solidify here, I'm solidifying almost pure nickel, because it's the higher melting point. If it was just for the copper here, if the liquid was all copper, it'd be all liquid. So that's something that carries on from one phase diagram to the other. So the higher melting point alloy in iron, between iron and the cementite, you get the iron as a higher melting point. And then you start solidifying, and then you can have a much purer material than your nominal composition. And then when we start applying that rule, so we start here, this is our nominal composition, and we're forming almost pure nickel, and we go down in temperature is where these equilibrium conditions change, and the liquid average composition is going this way. So in the liquid phase, I'm going to continue to have more and more copper, because that's how I reduce my melting point. I started here, and this is where I was starting to solidify, but by moving it in composition, I can be liquid at a lower temperature. It's really the basic point with some of those phase diagrams, and I realized after the class yesterday that didn't necessarily get all the way across. So if I change everything here, and I do gold and silver, it's exactly the same. Higher melting point, you get purer. Lower melting point, you increase your concentration of silver in the liquid over time. There are not that many alloy combinations that you can put in any proportion. Here in the solid, it's going to be only one phase. They essentially have to be the same phase to begin with. So if we're talking about the phase center cubic, the black atoms on this one, which is the case for gold and copper, it's one of the requirements. Then the next one is just about the same lattice size, atoms that are somewhat similar in size as well. So there are a lot of limitations to make that happen. Now, one thing that's interesting here between gold and nickel is you'll start having that solid phase where for any composition here, you only have one solid, and then you have a phase separation at lower temperature. So there's a certain temperature where in equilibrium, it's okay to have all atoms intermix in the same lattice, and as you keep cooling down, your energy terms become more important, and then all of a sudden you have a separation. Of course, those low temperature separation will or will not take place depending on the kinetics. It's the same that what we've talked about with steel and aluminum. You need time when you're solid to make that separation take place. So I thought I'll bring it up because these are exceptions. There are a total of 7 combinations of elements, metallic elements, that will give you a complete solubility at a certain temperature. And even fewer that will give it to you at all temperature. I've shown you 2. So we did gold and silver, and we did nickel and copper. Yes?
All of those elements you just listed are all in the same area on the periodic table. Is there a reason for that kind of coincidence?
Yeah. So you need about the same density, about the same size of atom, so that you can fit in the same lattice. That's right. Brass. I'm bringing up brass because it's commonly used in plumbing. If I have a plumbing system that's made of copper pipe, so nowadays it's mostly commercial, residential, we do a lot of plastic pipe. I have valves, I have fittings that a lot of times are metallic. Valves, a lot of time are brass, and one of the reasons is it's easy to machine them at relatively high speed and with precision. And the reason is, well, things change with respect to that, but one way, traditionally, where you have this brass here, which is copper and zinc, there are multiple advantages. First of all, zinc is cheaper than copper, so you're reducing your price by adding the zinc here. But also, you start forming these other phases. You can see here you have a beta phase and you have a gamma phase in a range of 50-50 composition. The advantage of that is you can essentially use the 2 phases, and in this case have them be large, so you don't try to cool it off the way we were doing the aluminum alloy. And what it does, it's easier to machine. It's easier to machine a 2-phase alloy than a single phase. So, of course, this phase diagram is probably much more complicated than you'd like to see it, but you can already see some of the common feature with what I discussed. Melting point for zinc, it's only around 450. For copper, 1060. So in between, you have a variation. All right? And the only difference from what we've discussed about earlier is instead of just having those 2 extremes, now I have steps in between. I have other solid phases that correspond to another arrangement of the crystals. So if I'm anywhere between this region and this region is where I have a little bit of both. If I try, there's a range here. If you see there, you have some periodic transformation. You can go from a single phase to 2-phase. There's a possibility with this situation to get some hardening the same way we've talked about. It's not used a lot. It can be used in any alloy that you find a transformation that you can delay and then find a very fine microstructure that you can do dispersion straightening. Yeah, you could do it. It's just a question of whether it's important. The brass itself, one advantage, it's generally good for corrosion resistance. It's not toxic. So it's used in potable water. It has sufficient strength, but it's not really strong. It's actually soft, and that in itself is not a problem. Especially for this one, we're putting a plastic pipe. It's acting just like a barb connection. You're wedging a plastic on it, and it only needs to be stronger than the plastic, really. So that's not a problem. If we go back to our aluminum alloy, I was mentioning yesterday about adding about 4% copper, and that's really where we were here. We were in a zone where it's all the equivalent of the aluminum structure, except that there is some copper in it. And then as I'm going down in temperature, I get into this big central zone. and then I'm getting a little bit of two faces. And that's really what causes dispersion strengthening as opposed to the eutectic transformation that we're going to see for steel. So aluminum, we're right here, and we cross over from being single phase to the two phase. One phase stays just like it was, the alpha phase of aluminum, and then we have a compounded phase that has both aluminum and copper that starts to form, if you remember, very, very, very small particle if it happens at low temperature, and as you go to higher temperature, if you were to go and cool it down slowly, you could get big grains of that second phase. But that's not what we research for strength. So that's the entire diagram. And we have a zoom out here with the different types of non-equilibrium. So you can see this is the equilibrium phase, the top one. All the others are phases that become at equilibrium given the kinetics. They metastable phases, essentially. So they will form because when you have the noise in the microstructure, it will start to, eventually they combine and they'll be all together. Instead of disappearing, they grow from there and get towards equilibrium gradually. All right, well, why do we care? That's a project. I was only working 2 years as a consultant, and in my group, I think I was the only one that didn't have permanent residency and all those things that it takes to work on a project like this. But they needed me, so I went out and looked at the superstructure to hold this antenna or dish. What happens is you have an internal surface there that needs a very, very specific shape to condense any signal coming from the extra space. And it's essentially all condensed on the little sensor that's in the middle of this. So what my group was working on was essentially making sure that when you rotate in all directions the ditch to collect signal, you remain stiff enough that you're not changing too much your condensing power. And they did have some adjustments. There were a few electrical motors that will be, you know, if you're vertical, it's going to be pushing in a certain portion of the structure to make some corrections. But the less corrections you have to do, the better off you are, essentially. So it has to be really stiff. And one big component of making it stiff is use tubular structures. So you're looking here at maybe 10 different tubes coming together. And so it's a little bit of a truss assembly. And the idea is minimize weight, because this was the self-weight of that component was the majority of the reason why when you reoriented it, it was deflecting. So you want to make it lightweight and stiff. Now you could use steel. You would have to paint it, because this was going to be exposed to some atmospheric moisture condition. One of the reasons for not using steel here is these members were both in tension and compression. So it's a little bit like designing a bicycle. So if I'm designing a bicycle, aluminum really has its advantages, because for the same weight, I can have something bigger and I can resist the buckling better. So in terms of stiffness performance, even though the aluminum Young's modulus is approximately 3 times less than steel, because you're thinking about buckling and you need a certain thickness, aluminum was a very legitimate choice. Not without any issues. And by that I mean welding aluminum changes all that heat treatment. Everything that we talked about quenching and aging. And therefore, a lot of times you try to avoid these types of joints. I'm sure you've seen them on bicycles. what happens with this joint is, say this member is loaded in tension, compression, or even worse, there's a little bit of bending on it. You get a lot of stresses here at the toe of the weld, and that's an area where the material is a lot softer than the tube itself. So that's why a lot of times we end up designing tubes, and you'll see both if you travel across the country in the airports. You know, sometimes you come in an aluminum structure, you see a steel structure, and you'll see both. You'll see the case where it's welded all around. It looks nice. It's good for water penetration, but it gives you stresses in the welds. This design here has gusset plates, so it's a plate here, and you put a slotted in the tube itself, so you can insert the tube over a plate, and then you put the welds on each side. What allows you to do really is to load these welds in shear as opposed to tension. So it's used a lot for tubular structures. It's what will give you the best fatigue strength if you're going to have any variations in load over time. And again, the reason we do it is this reduction in strength of the aluminum and steel, but right now we're talking about aluminum when you weld. And I'm showing here some data that we used before on the project. We're going through the heat affected zone. So what happens is it's a cross section through a weld. So you have the weld here, which is property. So you can have some welding electrodes that gives you relatively good yield strength and ultimate tensile strength. So we're looking at a range of say 22 and almost 38 KSI. You go through the heat affected zone. So in this case, the heat affected zone is all the way from here to where you become stable again. So that's the zone where you had a change in the properties of the base material. It didn't melt, but it changed the property. And this, one reason I was bringing it up is exactly what you guys were wondering about last time. You said, so what if we keep it longer? Well, we're going to grow this precipitate bigger, or we put everything back into solution. If you heat high enough that you dissolve the little particles you created, you lower it down and you don't do the aging, after the fact you use the structure as is, then you have the lower strength. Yes?
For smaller frames like bicycles, though, you can re-age it after you weld it, correct?
You can re-age if you wanted to. I don't think it's done very much, but you're right. If you knew exactly the alloy, you could get into a certain temperature. One thing you will not be able to do is to correct for the portion of the microstructure where instead of re-quenching it, all you did is heat it and grow the particles. And that's a big part of what's going on here. Because to put into solution, it takes time. It's not a question of reaching the temperature. You have to leave it there to remelt essentially those circuit phase particles. So it's very typical that welded joints don't have the strength of the base material. And when I say they don't have the strength, we're talking a factor of 3, especially for cyclic loads. So it's very significant if you're doing a design. The aluminum design manual will give you just about 2 or 3 KSI of allowable cyclic stress for an aluminum joint like those here. Yeah, and it was a problem when they did this because you can size the members very large. A lot of the size of the design was based on stiffness. When it was coming down to some of the connections, there were a few between 2 plates. It's very nice to use plates because the plate allow you to load in shear, but you come into this situation here where this plate needs to connect to something else, and eventually you got the plate connected to each other, and they are going to be in tension, one with respect to the other, and that's where the low allowable stress. Yes?
What's the outer bubble made out of from the telescope?
You don't have panel. It's a fabric, and they have to replace it sometimes. And it's actually part of the design where there's really this terrible situation with wind that you tear your fabric, but the main structure stays there. It happens I've seen it, I don't know if it was intended, but I've seen it in the Houston area after hurricanes where the posts are still there for advertisement, but there's nothing left, yeah. Safe fail, safe. I mean, it goes flying, but the whole post doesn't fall is the bottom line. We consider this, I worked on the design of the wind turbine that's at the airport where you have a shroud around it. So you not only have the blade to generate the electricity, and the purpose of the shroud, it's a little bit like the turbine engine. So you funnel the air in and you funnel the air out. And they wanted to consider that as an option to do the shroud as a fabric, so they wouldn't have to worry about the worst case wind. But there were other issues. It was very hard with the fabric to keep a very tight geometry at a reasonable cost. Yes?
So back on your the welding structure that you had break down the plates at the end for sure, doesn't that also result in the plates being in tension that are welded to the main struts?
It does. So what you do there, this is a good question. So why are we wondering about this? The two reasons is tubes are long, and therefore if you increase their thickness significantly, it's a big difference in weight. So relatively speaking, the plates can be thicker and not change the overall weight as much. The other aspect is, say a typical design was, I have a plate here, and I'm going to connect a tube, say on this side. So I got a tube coming in. I may have a tube coming there. And if I want a tube there, then I put a plate, say like this. And I come and weld from this side. Maybe I can do a little bead here. And then I have my other tube here, going this way. So this is a tree connection system. What we did between plates is we had groove welds. Groove welds, yes. Groove welds are different from fillet welds. So a groove weld on a flat is essentially, I take a piece with an angle, I leave some room for my material. Say I'm just going to do one side here. When I come and weld, I'm filling all the space. So this is all solid. So geometrically, I don't have a stress concentration. On a fillet weld, the main difference is most of the time, I am going to have one member coming one way. So say that's the tube, and it's welded to another tube here, and who knows exactly what's going on. So I'm putting a fillet weld here. So out of this geometry, I have a lot of stress concentration. Stress goes from one tube through the weld to the other one. It's very higher local stresses than if I'm just going through my member like this. The other example of a fillet weld is that ties better in the difference between the two is, say, a T-connection. So if I have a T-connection here, and I only use fillet welds, I don't have anything here, so I essentially have a crack in the metal because I didn't prepare it. So the strength of this connection for fatigue is about half the strength than if I did a T-connection with a groove design. So what the groove design lets me do is I come from one side and I fill it in here, and I come from the other side, I fill it in. So I don't have a pre-crack in this configuration. So I can do a groove weld here between those two components, but I couldn't do a groove weld if I try to get one tube with the other. Not just because of the angle geometry, the thicknesses are too low to really allow for it. At low thicknesses, you always end up with either a lap or a fillet well. Anything else? Yes.
So this is clearly chosen over fastening. What would be a situation that you would actually go to, like mechanical fastening instead of welding? How big?
I would say, so you would use fasteners on a large structure if you have to take it apart a lot. So in the example of a wind turbine, for example, you can have 3 segments of the big assembly that are made in the shop with welds, and then you're going to bolt these segments together out in the field and raise it up. And there are multiple reasons, and one is cost. So and we mentioned that earlier, that welding is very cost effective. You put the pieces together, you don't need to drill. It makes fluid tight joints. If you weld all around here, when it comes to the time to do the painting job, there are no issues. Allows you to cover a large area of contact very quickly. If I use bolts on a situation like this, I'm looking at putting many. You know, I need quite a few on top, I need quite a few at the bottom. And it's very hard to be as stiff unless you really tighten every fastener and it becomes a slip critical connection. You always develop more movement in a bolted connection than when everything is really welded. For fabrication, welding can be really amazing in the sense that if you're not building, you know, a spacecraft and you can afford a little bit of variation, say I'm making one structure just a tower and I have a little problem, I can, you know, hammer down, bend a little bit. The steel is very resilient to any small changes and adjustment. And if I'm bolted, I'm going to take the bolt out, I'll move the hole a little bit. You know, just getting the 2 pieces to line up is very difficult. I've seen cases where, say, field welding was not desired. Even a lot of times for building erection, they'll still bring the welder because they don't have to go out in the field and drill holes. But say they decide no field welding. So a lot of times what they do, if they have big braces, I'm thinking right now of the nuclear waste treatment facility I was working on. They need a lot of braces for seismic loads. And they didn't know exactly how square the building was going to be. So these braces came with the attachment plate, with essentially a gusset plate that was welded to the tube already. But between that plate and the structure, they had to put bolts, but they didn't put the holes. So it was out in the field, you had to drill through an inch thick steel to go across and then put the fasteners in. It's not terrible. There are drills that will have a magnet and hold on to the structure, and therefore it becomes like a press drill. But it's still multiple operation as opposed to the welding expert just coming on and covering both sides and let's go home kind of situation. All right, well, I think you guys now understand aluminum welding. Thank you, Chair. And we will move back to steel. I'm glad I covered steel already quite a bit. You guys understand there's a big phase transformation. It's the whole microstructure that's changing from that austenite. 2, 5, 6, 4. We'll give you the whole thing. I remember when I was an undergrad, one of my research advisors asked me, what do you remember the most of your, I was a senior year, what do you remember the most of your material science education? it's kind of a general loaded question, and my general answer was, well, the relationship between the structure, the processing, and the mechanical properties, that triangle or pyramid that I showed you at the beginning of the class. Well, his answer was from back in his days was the iron carbon phase diagram. That was the highlight of his whole undergraduate education. So if I bring it up to you for the third time, just excuse me on that basis. It's kind of an old technology. It's been around for a long time, yet it's still used quite a bit. And you get it a lot from Professor Eger's class in terms of how much volume of steel we use and different kinds of steel. So we're showing the diagram here, probably for the last time, where we go all the way from 0 to 6% carbon, and we have the cementite here at 6.7%. So that's a very hard particle, intermetallic, if you will, here. And what happens is you got these two regions where you can have some transformation. The lowest temperature liquid is the cast iron here, and that will give you the eutectic transformation back into austenite and cementite, and there are a lot of different cast irons. I only giving you a brief overview to say we use them, and we can make them ductile. I've shown an example of that, but we didn't emphasize too much this portion of the diagram. Everything here is a lot of phase transformation. We're not talking about precipitation or hardening. We're going from a liquid into two different solids of two different composition. And we can have extra transformation. So you form the austenite, the cementite. When you go to this temperature, you get an extra transformation in your austenite back into more phases. So these microstructures are very complex to look at. But they're very cheap to manufacture. You don't have to reduce the amount of carbon into your cast iron when you process the iron, and you can get materials that are very good for wear resistance. Some are very good mechanical insulators. There are advantages into cast iron, and they also make your piece all at once. That's a big advantage. I had these little fittings I showed you. You just cast it and you're done. With steel, we're in this range here. Most typically, we are below the eutectoid transformation temperature. So that is at 0.8% carbon. You can have a steel that's beyond 0.8% carbon, but it's really not going to be ductile, because your first phase forming when you reach that temperature is not the pure iron, it's the cementite. So you're creating a lot of hardness and brittleness in those steels. So the most typical one for structural steel, the largest volume is somewhere around 0.2% carbon. And you will go higher, maybe if we're thinking about a fairly high strength steel for a heat treatment, it's going to be around 0.45% carbon. And that would be a steel used for landing gears on aircraft. It goes through this whole process of quenching and tempering to reach a combination of strength and toughness. So what happens here, you start solidifying. If I'm making steel, I'm starting to solidify around 1600 degrees C. That's pretty, 1550, but it's very high temperature, and it doesn't solidify all at once. You see these curves going down towards that eutectic. So my microstructure has all these dendrites that we've seen when we were talking about the processing. So now you get a better idea, why am I getting all this complex structure? Because I'm having two components with a different melting point, and there's solubility, and therefore we do that mechanical deformation in that austenite region. That's where we really blend the grain, the microstructure, and get the composition to be the same. And then we're ready for our heat treatment. So our heat treatment starts in that austenite here, and when we reach the temperature here around 730 degrees centigrade is where we're gonna form the ferrite. So just pure iron, and the cementite if we go slowly. If we go fast, we miss it. So if we go slowly, everything changes in the microstructure from something like this to something like that, and the cementite. I forgot what the cementite is, but it's not deformable. If I'm going really slow and I had this, what happens is I'm just changing it a little bit, and the carbon goes into one plane, one direction, and that's why I become tetragonal. Because this doesn't want, there's little room here, it's very compact, there's very little room for carbon, and that's why it gets stretched, and you go through that martensite if you're cooling it off. All right. So, knowing all of this, you can hopefully understand better if we're forming pearlite. So again, we're going from this to the ferrite, and we have the cementite. This is ideal. This is not the exact composition, but assume for now that you go through it and it's the eutectoid. So it's the austenite on top transforming into two zones. We're going to have the iron, and we're going to have the cementite. So it happens simultaneously, and that's why you get that laminar structure. And we have some more laminar structure everywhere here. The spacing of these laminar structure is going to be much bigger at higher temperature, and that's why at the end of last class I showed you the nice pearlite structure with the different layers, because it was oven cool, which is not typical. Typically you take the piece of steel out of the oven and they get air cool and you get a finer microstructure. But if you go it more quickly when you do it more quickly, you can essentially adjust that spacing and the strength of the pearlite. Now let's go to something that came up. I was advising an intern this summer. She was processing materials, and I talked to her about phase diagrams. She said, yeah, it seems too complicated, but when we went to these time and temperature phase transformation diagram, she felt more comfortable. So we'll try that here. So this is now very different. Everything that used to look like different compositions is now the effect of time. So we have an alloy of a very specific composition, and what we're doing during cooling is we're studying what happens at what temperature, what time and temperature it's going to transform. Now, we're talking about relatively controlled cooling. So you go from the temperature A as an austenite, and then you're cooling back down to a constant temperature that's 620 right there, and you keep it there. That's not necessarily easy to do, so we're kind of having a little ideal situation here. But if we do that, what the kinetics tells us, it will take quite a bit of time to start having anything happen. And when you do, when you start forming that pearlite, the temperature you're at is what's going to dictate the size of these different lamella. If you're at higher temperature, you get more diffusion, it'll be more broadly spaced. If at your lower temperature, it's more intertwined, it's much thinner layers. So this tells you, okay, I'm trying to go from my austenite to the pearlite, the equilibrium phase. It will take a certain time, and this is how it's going to go. You can see it in that schematic. It is starting from the grain boundaries and moving inside the grains. What you can think of on the same schematic is if I want to avoid this transformation, it's visible in the schematic that I'm just going to continue right through it. I'm going to try to cool without having that transformation. So this is the most visual way to see that transformation taking place. You can have two versions of this diagram. This one here is the one where you're really controlling the temperature. There's another one that you can generate that would be based on more of a gradual cooling rate. So oven cool will tell you at what temperature you're actually going to form the different phases. The main aspect to this is to help you see why am I getting all these different phases. These are all essentially the same type of microstructure where you have alpha iron and you have cementite or you have martensite, depending on exactly what happens. Sometimes you can even temper the martensite. Furnace cool anneal. So this is coarser than this one, for example. So if I go to A, yeah, it's cool. It's cooled normally. Normalized, it's air cool, and the furnace cool gives you a much coarser microstructure, much bigger grains. The reality is sometimes you don't select this. I brought this today. If I'm trying to make these big axle for trains or big trucks, a lot of times I do care more about the properties on the surface, because if it's going to be loaded and bending, that's where the cracks are going to start to initiate. So I may be willing to tolerate a microstructure that's closer to this one in the core if I have something finer and higher strength on the surface and I get enough cooling at those locations. But a lot of times, because this is already fairly heavy, you will want to go through the entire process of hopefully you have enough alloying element here to oil quench it as opposed to water quench it. Because if I water quench something this big, I get a lot of distortion. And then I may need to go back and machining it, and that's very, very expensive and difficult. So the idea to add some alloying element to make the steel, you just see a bunch of cracks, and they all start from the surface. So it's here, 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 here. Those are the main initiation crack. You can pass that around. You guys are engineers, you're smart, just be careful. It's heavy. Okay, so 43, 30, 40. So that's exactly the type of alloy steel that I was talking about earlier for landing gear. What happened here is you have 100 seconds. You have quite a bit of time before you start forming any ferrite or any cementite in your alloy. We're here at 1,000 seconds. That sounds pretty reasonable. 20 minutes, right? I've got 20 minutes to cool my low alloy steel and avoid the transformation of the pearlite. That's much better than, you know, seeing all these differences between, that I was just showing between, oh, I cool it in the oven and I cool it in the air, see how different it is. So by adding a little bit of nickel, chrome, there are other alloying elements. What you do is you delay the transformation. These are extra solid solution pieces in the austenite that will not fit nicely in any of the other structures, and therefore it's preventing it. It prevents the initiation of the transformation. The biggest advantage to this is you minimize the amount of residual stresses or even the risk of distortion cracking, and you can start forming that martensite that we've been talking about yesterday. You form the martensite, and then you can heat it back up for the tempering treatment. Now, I didn't talk too much about the tempering treatment, but it is effectively like precipitation hardening. So we have that martensite, it's very unstable. Depending how I heat up is going to define how fine is going to be the separation now between that martensite back into the ferrite and the cementite. So you're going back to the equilibrium phases, but it's going to be at a very, very fine scale, and therefore you still have strength. That's just a view of the martensite. And you will get it on a low carbon steel on the surface. But even if I take a sheet of carbon steel and it doesn't have any nickel or carbon in it, nickel or chrome or other alloying elements, it doesn't go easily into martensite. And that's why it's good for welding. Because when you weld it, you heat it up and you cool it back down, you avoid forming that brittle phase. You can't go fast enough. The 4340, that example I was looking at, if you're going to try to weld this, you need very sophisticated procedures. You need to preheat the steel, and a lot of times you need to go after what the preheating does, it's preventing you from forming cracks. So even though you can form some relatively brittle phases upon cooling, it's overall your material is going to be soft enough that it will deform instead of cracking. And then after the fact, you have to go back to eliminate the martensite that you created, and that's the post-weld heat treatment. So you have to do the tempering after you welded these steels. So Professor Egers typically says that most materials are weldable, and then it becomes a question of how difficult it's going to be. And the more you put alloying element, the more you're likely to form that martensite, and you have the brittleness. And then the question is how to get rid of it, and the post-weld heat treatment is the solution in that case. Yeah, this may be a good point to stop, and I'll continue on Friday. Tomorrow, Professor Eger is coming back to continue his part of the module. Thank you.